In a certain region of space, the electric potential is given by V equals y squared plus 2.5xy minus 3.5xyz. Okay? Determine the electric field vector. Boom. So one important point here is this electric potential is a scalar. We want to convert this scalar into a vector. Vector E. In this region, express your answers in terms of the variables x, y, and z separated by commas. Commas? Commas. Okay. English is my first language. I don't know why I have trouble with that. Okay. So, let's go back to our Wikipedia. So we have electric potential up here, and we have voltage equals negative integral E dot dl. So that's of moderate importance for this. So V equals negative integral E dot dl. So it's a dot product here, and we have a dot product between two vectors. So that defines the voltage. Now, you might be like, all right, we're not looking for voltage here. We're looking for the electric field. And so the way we find the electric field then is we basically take the derivative of both sides. Now, when you're talking about vectors and scalars, the nuances of what defines a derivative is a little bit shaky. Long story short, the electric field equals the gradient negative of the voltage, electric potential. So make sure, yep, right here. E equals negative gradient, is the gradient. Electric field is conservative and determined by the gradient of the potential. Okay? So now we know what the gradient is. At this point, we need to find out how we use the gradient in this case. So, okay, so this isn't too bad. So the gradient will be, we'll take the derivative with respect to x. So we'll do it like this. Partial derivative with respect to x of voltage, and that will be the x component. And then we'll take the derivative of, there's different ways of writing this. I'm going to write it as plus. And instead of the answer they want it separated by commas. But this, I'm going to write it in terms of the unit vectors. Same thing, it's just a different style of writing. So take the partial derivative with respect to y of the same voltage we have, and we'll make that a little y hat. Do a partial derivative with respect to z, and we'll do voltage, and we'll make a little unit vector z. So I say hat sometimes, hat, unit vector, same idea. It's basically this gives you the direction. So you'll see as we go. Okay, so this is what we need to keep in mind right here. So I'm going to rewrite it as negative v equals negative y squared minus 2.5 xy plus 3.5 xyz. So I rewrote it because I want to make sure I don't forget the negative sign. And it'll make it closer down to here so I can zoom in. Kind of convenient. Okay. So, ooh, green. Gray. I'm going to do gray. Gray is an underappreciated color. So, I'm going to do it this way. Electric field equals x hat times. So now we're going to take the partial derivative of the voltage with respect to x. So we'll have negative 2.5 y plus 3.5 yz. So when you do partial derivatives, you take a derivative with respect to what you're taking a partial derivative with respect to, but you hold all the other variables constant. So here I'm pretending as if y and z are constant, and I'm only taking derivative with respect to x, which is why this negative y squared goes away. Then we'll add to this the y component vector, so we'll have negative 2y, no, just negative 2y, no squared, minus 2.5x plus 3.5 xz. Because this is y to the first, derivative of y to the first with respect to y is just 1. or 1 times y to the 0, which is, again, 1. Z hat, okay, so now we'll do the z portion. So that goes to 0, that goes to 0, and we are left with 3.5x y. And this will be our electric field that creates this potential in this space. So express your answer in terms of variables x, y, and z separated by commas. So here's our electric field. It is a vector. You have a little vector sign? Yep, vector. And we're doing it of component, making it part of component vectors, x, y, and z. And so the first part here would then just be negative 2.5y plus 3.5yz, separated by a comma, and then the y, and then the z. So this is ex, this is ey, that is ez. And that's how you convert from potential to an electric field. And then if you wanted to go the other direction, your potential equals negative integral E dot dl, which I'm sure we'll do in other problems as well. It's fairly common. I'm sure we'll get to it. So hope that helped. I will see you on the next problem.